All right, so chapter 15 is kind of split up into two sections. The first section is about something called a buffer, and so we are going to talk about what buffers are today and talk about the problems associated with that. The second part of chapter 15 is about acid-base titration, and we've done a little bit of simple titration stuff at the very beginning of the year and even last year, but it's a lot more in depth. So that's the second part of chapter 15. So start with buffers today. Okay, so to understand how buffers work, you need to understand something called the common ion effect, which we've seen just a tiny bit in chapter 14. It came up in one of our free response questions. And it is the idea that you combine two chemical solutions together that have a common ion. And so in this particular example, the example is the weak acid is hydrofluoric acid. The salt that has the common ion is sodium fluoride. What's the common ion between those two? Yes, the fluoride ion, okay? They both have a fluoride ion, so that's the whole common ion thing. Now, when you combine things together that have common ions like that, it changes the whole equilibrium process just a little bit. And so if we think about these two compounds separately, if I have hydrofluoric acid, it's a weak acid, so it will ionize, but just a little bit. And it'll ionize into hydrogen ions and fluoride ions. Sodium fluoride is a salt, just like a solid salt, like the salts that we used to make the solutions last week. So sodium fluoride, when I put that in a solution, will ionize. It's a soluble compound, okay? They're not going to try and trick you and give you compounds that aren't soluble. So this is soluble, which means it's going to break apart into sodium and fluoride ions. What's going to happen is this fluoride ion kind of comes in here, and if you put some sodium fluoride in a solution of hydrofluoric acid, you're going to end up with a starting concentration of fluoride ions. Remember before, like when we would talk about the ionization of a weak acid, and we would set up our ice table, and we would have, a certain concentration of hydrofluoric acid, and then this would be 0, and this would be 0. When you have this whole common ion effect, if I take sodium fluoride and put it in the solution of hydrofluoric acid, this starting concentration is no longer 0. It's a certain concentration that you have to figure out. And then that changes the problem a little bit. A common mistake that you need to make sure you do not make is, the problem will say something like, I combine two solutions together. I combine hydrofluoric acid and I combine sodium fluoride. And you have to write out the equation for the reaction. People will sometimes think, okay, well, if I take HF and sodium fluoride and I put them together in the same solution, then those both become reactants. That is not correct. Those do not both become reactants. It's more of this situation where you have two equations that happen separately, and when you're writing out equations for this situation, the weak acid dissociation is going to be the main equation, and the fluoride that comes from the salt will come in here and instead of being 0 be a number. So you don't write them together as products. These two things, hydrofluoric acid and sodium fluoride, Sometimes they refer to them as being partners because they have the same ion. Partners have to be on opposite sides. They can't be on the same side of the equation. They both can't be reactants. So just don't add them together. Now adding sodium fluoride to the solution adds fluoride ions to the product side, limiting the forward reaction from happening. Because if this ionization wants to produce hydrogen and fluoride ions, if there's fluoride ions already there, then it's not going to take as many fluoride ions to reach equilibrium. So that forward reaction doesn't happen as much, which means also you get less hydrogen ions. So it affects the pH and the percent ionization. All right, so this is from chapter 14. I'm going to split that up. It looked like it says 14%, but it doesn't. What? Yeah. Okay, so from chapter 14, oh, you would also be given like the Ka value. From chapter 14, this was on your test. It was a different acid, but it was the same idea. You guys had to find the percent dissociation of 0.1 molar acetic acid. Okay, so basically what you would have, we're not going to write all this down because we talked about it in chapter 14, but you would have x squared over 0.1 minus x equals 1.8 times 10 to the negative, not 15, 5. And then you would solve for x, and x is the hydrogen ion concentration, and you can figure out percent ionization from that. The percent ionization of 0.1 molar acetic acid is 1.3%. Okay, so what we're going to do is we want to compare that to figuring out the percent dissociation of a mixture that contains not only the weak acid, acetic acid, but also 0.1 molar of a salt that has a common ion, sodium acetate. If you set up for the ice table for this, the initial concentration of acetic acid is 0.10 molar. The initial concentration of hydrogen is 0. Now normally when it's just the regular dissociation of acetic acid, this would also be 0. But when you throw in a salt that has a common ion, this number is no longer 0. This number is whatever that concentration is. So 0.10 molar is my initial concentration of the acetate ion. So that changes your setup a little bit when you solve for x. You still get plus x right here, but now you have 0.1 plus x, and then 0.1 minus x. Okay, so we've done problems like this before. You would have to solve for x. You would do products over reactants and set it equal to k and solve for x, and then you could calculate the percent. When you calculate the percent based off of this ice table, you get 0.018%. Okay, so we're doing all of this just to show you that the presence of a common ion affects the percent ionization. So Normally, acetic acid has a percent ionization of 1.3%. But if I throw some acetate ion in there to start with, it hinders the forward reaction because it's already closer to equilibrium here than it was without this starting concentration. So, it doesn't dissociate as much, so you don't get as much hydrogen, and it affects the percent ionization to where it almost doesn't even ionize at all. 0.018 is a very small percentage. So more common ion means less dissociation of a weak acid. It's this common ion effect that is the idea behind what a buffer is. So let's talk about generally what buffers are, and there are some problems that go along with that too. Alright, so we're going to be doing a whole lot of calculations involving buffers. And then as we go through all of those calculations and we do the rest of chapter 15, there's always like this thing at the end of the chapter where people are like, wait, we did all this math with buffered solutions, but like really, what is a buffer again? So just remember that a buffer is just a solution. Just like the solutions that you made up last week where you have some kind of solvent and then you put some solute in there and it dissolves it. It's just a solution. And it's a solution where the pH doesn't change very easily. So you can add stuff to the buffered solution and the pH will stay pretty consistent. And it's because it has a whole common ion effect thing, so it doesn't allow as much dissociation, and so pH doesn't change. A very common, important buffered solution is our blood and other stuff within our body. I mean, there's certain enzymes and things that won't work properly outside of certain pH ranges. And so our body has to be able to keep that like steady. And so that is an example of a buffered solution. The pH doesn't change no matter what you add to it. And so next week we're going to be actually making buffered solutions, and we'll add acids to it, we'll add bases to it, and you'll see that the pH changes very minimally compared to if it was not a buffered solution. So what is used to make up a buffer solution? There's a couple different things. You can have a weak acid. Okay, if you have a weak acid like the one example that I gave you, hydrofluoric acid, and then you add a salt that has the common ion, sodium fluoride. So that's what the partner thing is. It's a salt that has the common ion. Or it could be made with a weak base, like NH3, ammonia, and a conjugate acid partner, which it always has to be a salt, so maybe it's ammonium chloride. Okay, so ammonium, NH4 plus, and NH3, those are like considered common ions, they're partners. Significant quantity, when it says it has to have a significant quantity of the salt partner, that means within a factor of 10, which is, I mean, you're not going to get any problems that are outside of that range. So you don't have to worry about that so much. An ideal buffer is going to have the same concentration of both. So I would have the same concentration of NH3 as I have of the NH4Cl. That would be considered an ideal buffer. All right, so let's go ahead and do a calculation. There are questions where you have to calculate the pH of a buffered solution, and then there's some questions where you have to figure out how to make a buffered solution, so we'll do each. Okay, so calculating the pH of a buffered solution. Here we've got, you need to calculate the pH of a solution where you have 50 milliliters of 0.5 molar sodium acetate. It's mixed with 25 milliliters of 0.2 molar acetic acid. And I have to figure out what the pH of that is. Now, a couple things. I mean, really, we're going to do it the long way first, and then I'm going to show you the shortcut way. But I want you to see why this works the way it does. It's basically an ice table problem, okay? So if this is whenever you're dealing with buffers, the equation that you write the ice table for is the weak acid ionization. So acetic acid, hydrogen ions, acetate ions, and then I'm going to have starting concentrations of both, and you'll solve for X and figure out the pH and do all that. But you'll see that I'm mixing two solutions together. Now, there was a question on your test in Chapter 14 where we mixed two strong acids together, and you had to figure out what the new molarities were. This is kind of the same thing. So I'm mixing two solutions together. I have to figure out what the new molarities of those things are when I mix them together to make 75 milliliters of the solution. So for sodium acetate, if I do M1V1 equals M2V2, okay, I've got to do all of that. My M1 for sodium acetate is 0.5, my V1 is 50, and then I'm looking for M2, and then my second volume is the combination of those two, that's 75. So I get M2 equals 0.33 molar. That's the concentration of the acetate ion. So my initial concentration over here when I'm setting up my ice table. And then if I do the same thing for acetic acid, and I do M1V1 equals M2V2, M2 will equal 0.083 molar. Okay, this is 0. Then it's just an ice table problem, so minus x plus x plus x. When you solve for x, it is the hydrogen ion concentration, and that's 4.5 times 10 to the negative 6. So then you negative log that to get the pH. pH equals 5.35. Okay, so you can do it this way. And really, I mean, we've done this problem before. The only difference is that this isn't 0. And so you really already know how to do this. But this is kind of a long process. And so there is, when you're dealing with buffers only, you can't do this with just like weak acids or weak bases or whatever. You can only do this with buffered solutions. There is a special equation called the Henderson-Hasselbalch equation, which makes this process to calculate the pH a lot easier. Okay, so here's the equation. This whole thing, if you are going to calculate the pH, oh dear. If you're going to calculate the pH of the buffered solution, that equation is pKa. Now if pH, when you calculate pH and you have a hydrogen ion concentration, you know that it's the negative log of the hydrogen concentration. So what do you think pKa would be? Anybody? Anybody? Negative log the Ka value, which would be given to you of whatever the acid in the solution is, plus the log of the initial concentration of the base over the initial concentration of the acid. So if I were to plug in all these numbers for the problem that we did up here, the pH would be equal to negative log of 1.8 times 10 to the negative 5th plus the log of my base concentration is 0.33 and my acid concentration is 0.083. Okay, get out your calculators. If you don't have your calculators, get them out. I want you guys to plug this in and see what you get as your answer. Okay, do it. Calculators. Okay, you should get 5.33. Which if you compare to the answer that I got up here, which is 5.35, I mean, really that is the same answer. And so this equation is a lot easier than having to set up ice tables and having to do M1, V1 and all that stuff. And there's even a better way to do this, because here when I plugged in the concentration of my base and my acid, I still had to do M1V1 equals M2V2 and figure out those new concentration values. But there's a shortcut to that as well, and that is using something called millimoles, which we haven't used before, but I mean, it's not like we've used milli of other things. If molarity, just kind of write this off to the side or something, because using millimoles is really helpful when you're dealing with buffers, and it makes the calculation go a lot faster. So if molarity is moles over liters, that's the same thing as saying millimoles over milliliters, just making everything milli instead of regular units. And so what you can do is, if you take the molarity times the milliliters, okay, that takes away having to convert to liters and all that stuff. Molarity times milliliters equals millimoles. Okay, so like if I do my sodium acetate up here, my molarity was 0.5, my milliliters was 50. That's 25 millimoles. If I do the same thing for the acetic acid, it's 0.25 times 25, and that's 6.25 millimoles. Okay, the reason why this is helpful is because if you just take that millimoles and you plug it in instead of the concentration, it will work just fine. And you don't actually have to calculate the new concentration, because if you were to calculate the concentration of this, you would be dividing it both by the same number, and you'd end up getting the same ratio and all of that kind of stuff. So you can just take millimoles. You can take moles too if they give that to you in the question. I think in the homework they do. So my millimoles is 25 for, that is the base. So I would plug that in here. And then my millimoles for the acid, I would plug in right there, and you would still get 5.33 as your answer. Okay, so I'm just going to give you one to practice with, to do on your own real quick, using the Henderson-Hasselbalch equation and figuring out which one is the base and the acid. So calculate the pH of the following solution. You have 25 milliliters of 0.150 molar hypochlorous acid, which is weak. That was on some of your tests. With a that weak acid has a Ka value of 3.5 times 10 to the negative 8. And then you have 32 milliliters of 0.45 molar potassium hypochlorate. Okay, so the hypochlorate is the common ion. Calculate the pH of that. Okay, so remember to do it with millimoles. So just remember milliliters times molarity equals millimoles. So you can do that for each one. Plug it into the Henderson-Hasselbalch equation and see what you get for the pH.